Let's take a second and talk about impulse. Um, Now, first, let's review. Momentum is one of the properties an object has when it's moving. Another property a moving object has is kinetic energy. And kinetic energy is the amount of work that that moving object can do onto something else. In order for an object to use its kinetic energy to do work, going back to the definition of work, it must apply a force through some displacement. Where does this force come from? This force comes from the object's momentum, but more specifically, it comes from when the object's momentum changes. This force is the result of an object's change in momentum. So when an object changes its momentum, it applies a force to another object that can do work. And that's the relationship between momentum and kinetic energy. It comes through the change in the momentum or impulse. And so the question becomes, how do you change an object's momentum? Momentum is simply mass times velocity. So you either change mass or you change velocity. The simpler way is to change an object's velocity. You can change its mass. That gets a little bit more complicated. So let's just focus on changing an object's velocity. So here we go. Here's our momentum equation, except I rewrote it as the change in momentum, delta P, is equal to mass times delta V, our change in velocity. That's kind of a nice little equation. Let's go back and think about the basics for a second and look at acceleration as an object's change in velocity divided by some time period. And I can rewrite this equation to express it as an object's change in velocity is simply acceleration times some time period. Now, sticking this expression, acceleration times change in time, into my first equation that has change in momentum, gives me that an object's change in momentum is its mass times change in velocity, and that's also equal to mass times acceleration times change in time. And we know that ma is equal to force. And so an object's change in momentum is ultimately equal to some force times a time period. Now, just to kind of back things up just for a second. Newton's second law of motion. Newton originally expressed his second law of motion in terms of force related to how much an object's momentum changes. That's his original expression for his second law of motion. We apply an argument similar to this derivation to back up to say that force is equal to ma. So that's kind of the relationship between Newton's second law of motion and impulse, or change in momentum. Impulse is the object's change in momentum. We give it the symbol J. I don't really know why. If you want to score some extra points, look it up. Tell your teacher, hey teacher, I know why impulse is given the symbol J. They'll love you for it. And so here's our equation for impulse, that J is equal to change in momentum, which is mass times change in velocity. The change in velocity is final velocity minus initial velocity. And so we can rewrite this as mass times final velocity minus mass times initial velocity. And as we already know, the change in momentum is also equal to force times some time period. Since force is a vector, velocity is a vector, impulse is a vector. Impulse, the direction of the impulse is in the same direction as this force, because this force is causing an object's momentum to change. The direction of this force is going to be the same direction as the object's change in momentum, which is impulse. So when we say impulse and change in momentum, they're the same thing. Let's take a look at our impulse equation for a second, and let's just point out some things about it. Mass and time are scalars, and because they're scalars, they have to be positive. Final velocity, initial velocity, and force are vectors, And so when we're working with these parameters, we have to indicate the direction. Now, in my class, I just look at positive and negative direction. We don't get into direction in the x and y for these calculations, although you certainly could. Force is the net force that's causing the object's change in momentum. If you have several forces acting upon an object, you have to look at the overall net force in order to properly calculate the change in momentum. The direction of the force and the direction of the final velocity are going to be in the same direction if the final velocity is not zero, if the object is not stopping. If the final velocity is zero, it has no direction. So in that case, if the final velocity is zero, force and initial velocity will be in the opposite direction. It has to be because that's what the force is being used to stop the object. Last thing to keep in mind, we have to use SI units. In the conservation of momentum with mass and velocity, you don't have to use kilograms for mass and meters per second for velocity. It doesn't matter what mass and velocity units you use as long as they're the same throughout the equation. Here, because we're dealing with newtons, we have to use the SI units. So keep in mind, mass has to be in kilograms, velocity has to be in meters per second. Time is always seconds. Okay. When objects interact, impulse tells us how one of the object's momentum will change. Now, conservation of momentum looks at all the momentum of objects before they interact and all the momentum of the objects after they interact. Impulse tells us what's happening to a specific object during the interaction, and it tells us how that object's momentum will change. Impulse explains why follow-through is important in sports. A longer contact time for the same force gives us a greater change in momentum. Impulse explains why when these stuntmen jump off buildings, they land in these big air mattresses. We want a small force for a long time period. They don't have to use one of those big inflatable mats to land on. They can land on the sidewalk, in which case we have a very large force for a very short time frame. That's not a good idea. So they like to use a small force for a big time frame. Kind of the same idea as an airbag in your car. Keep in mind that for the same change in momentum, for the same delta P, we can apply a large force for a short time period or a smaller force for a longer time period. Here's the idea of airbags, cushioning when you get hit, that type of idea. So impulse, nice expression that tells us how an object's momentum will change. It's related to work through force. It's related to Newton's second law of motion. It's also related to momentum and conservation of momentum. But momentum, conservation, and impulse are all slightly different things.